I'm Zoe, and this is my physics lab 1. I mean, lab 6. Lab 1. Any, oh, okay. Introduction. So the purpose of this was to explore the phenomenon observed when a powerful magnet is dropped straight down a conductive non-porous tube and falls out the other end. The result preview. So some things with our experiment, the initial conditions involve a bar magnet and the stopwatch starting at 0, and then the system is the bar magnet and the aluminum tube, and the surroundings or everything else. The experiment time was 1.64 seconds, while our computation time was 1.13, which is less seconds. So some fundamental physics principles. First, the Savart law, which looks a little funky in here because the layout, but I mean, we should be pretty familiar with that by now. And then Faraday's law, which shows the EMF as equal to, it's equal to the derivative of flux. And then Newton's second and third law, F equals ma, and then every action has an equal and opposite reaction. Oh, this EMF is actually equal to the negative derivative of flux, but since we're finding the absolute value, it doesn't matter for that. Okay, the observed model. So this is our experiment. You can see we put the magnet down the tube and it, oh, so, okay, well, you should see that the magnet comes out the end of the tube. I don't know why it's doing that so weirdly, but, and then so here are 5 trials, and then our average time, as I said before, is 1.64 seconds for traveling. The So for this, we need to know the mass of the magnet, and then we also need to know the tube length, diameter, radius, and thickness, which the length is 0.46 meters, the diameter was 0.03 meters, the radius was 0.015 meters, and the thickness was 0.0051 meters. The computation model, so this is for the magnetic field, using Savart's law, which I mentioned in the fundamental physics principles, and this is the calculation of the flux, which I also talked about, and then here's some of the other calculations we did with magnetic force of the magnet and net force, as well as updating the magnet's velocity and position. So here's like the result showing the time and also just what it looks like when you run the code. Okay, so what if the resistivity of the conductor reduced as close as possible to 0? How would the dynamics of the falling magnet change? Low resistivity results in bigger currents and stronger braking, resulting in a very slow fall. And then if the holes or slots were cut into the tube, how would this affect the ring currents in your model? The slots and holes result in weaker or broken currents, which results in weaker braking and a faster fall. And that is all, folks.